All right, ladies and gentlemen, this class recording has started. So, at the beginning of our last unit, we introduced the concept of an isotope. One of the questions on your exam was to discuss the similarities and differences between two isotopes. We can really sum it up basically in two concepts. So what makes isotopes similar to each other? Donna, go ahead. They have the same number of protons, which also means they have the same electrons. I was thinking of something else. The number of atomic number, right? So they have the same atomic number and the same number of protons. But they are different in that... Go. They have a different number of neutrons, or they have a different mass number, right? So this is a concept from last section, right? They are atoms that have the same number of protons, but a different number of neutrons. And that means they have the same atomic number, but different mass numbers. Okay? And to fill in your outline, right, they're the same element, but they have a different mass number, right? I changed a couple of things on the outline because I thought it made a little more sense. Or I changed a couple of things in my presentation because I thought it made a little more sense. So there are things that might not match up with your outline. I'll try to make sure that I tell you when that's the case. All right. I made a big deal in the last section about when we talked about the mass number is not the number that shows up on the periodic table, right? There are two numbers that show up on the periodic table, right? The atomic number that tells you about the protons and electrons, and then there was like a decimal. And I made a big point to tell you that that decimal is not the mass number. How do I know that? Because what does the mass number do for us? What is the mass number of an atom? Okay, good. Number of protons plus the number of neutrons. Meaning, we are in effect counting, right? Mass number tells us the number of protons and the number of neutrons. It's a counting value. It is always an integer value. But if you look on the periodic table, that other number that shows up is generally not an integer, right? It's some decimal. That number on the periodic table is related to the atomic mass. I realize that they both have mass in them, but they are two different things. So let's talk about that other number on the periodic table. First, we discuss the atomic mass. Atomic mass is a relative scale. Okay? Like I said, I changed some things around in the outline, so if you have a question, just raise your hand and we'll get it straight. Okay. All right, what do relative scales do for us? Or what are relative scales good for? Okay, good. Comparing. Relative scales are not absolute measurements. They are comparisons. That number that shows up on the periodic table is not a measurement. And when I say that number that shows up on the periodic table, do we know what I'm talking about? Right? Here, let's do this. Don't look. I don't want to ruin the surprise. Let me do this, and let me do this. All right. So, when we talk about the number on the periodic table, right? I should go here. I'll sit down so you can all see the screen. Sorry if I'm making you dizzy, everybody. Apologize. All right. So let's zoom in here to lithium. That is terrible focus. There we go. Okay. All right. So here's lithium, right? That's the symbol for lithium, right? Capital letter, lowercase letter. Remember when there are two letters, always first one's capital, second one's not, right? There's the name. This number up here is the what? That's the atomic number. And then this one here, right, as it says over here, is the atomic mass. That's actually a little misleading, and we'll talk about why here in just a little bit. But when I say that other number on the periodic table, that's the one I'm referencing, right? And most of them are decimal values. We'll see that some of them come out to be pretty close to whole numbers, but most of them are decimals of some kind. Okay? Good there? Just want to make sure when I say that other number on the periodic table, we know what I'm talking about. All right. So let's go back to our presentation. So atomic mass is a relative scale. Like we said, relative scales are good for comparisons. Atomic mass compares the size of atoms. But if we're going to compare something, we have to have a standard to which we compare all the other things to. Right? Yesterday, when you guys did your bean lab, what did we compare all the other beans to? The median, or the one that had the one that was in the middle, right? And that gave one of our values of 1, 2 that were less than 1, and 2 that were greater than 1. Does that sound familiar? Hopefully yes, right? So we were comparing all of our beans to the one that was in the middle, average-wise. Atomic mass compares atoms, but it compares all of the atoms to one specific atom, and that atom is carbon-12. Okay? First, you should be able to tell me 3 things about a carbon-12 atom. Oh, my bad. Freeze for a second. If you don't have your periodic table out, pull it out, please. Sorry, it wasn't on the list of things at the beginning. We're going to use it today. Apologize. It's a nice little break for you guys. And if the person next to you has a periodic table, that's fine too. If you don't have yours, you know, you can share. I suppose if the person next to you isn't a jerk, you can share, you know. But. All right. Based on our activities from the last unit, you should be able to tell me 3 things about an atom that we call carbon-12. All right? So, take 30 seconds, talk to the person next to you. What do you know about this atom that's carbon-12? Go. All right, let's discuss. So, what's one thing that you told me, or that you discussed about this atom that we call carbon-12? Charlotte, what's one thing? 6 protons. We know that why? The atomic number of carbon is 6. Liam, what else? 6 electrons. Why? It has to have no charge. So if it has 6 protons, it's got to have 6 electrons. What's the third thing you can tell me about carbon-12? Austin, go ahead. 6 neutrons. How do you know that, Austin? No, you do not take the atomic mass and subtract it. What do we... No, you take the mass number and subtract the atomic number. What's the mass number of this isotope? 12. That's why it's carbon-12. Okay? Good there? Keep that in mind because we're going to have to do that several more times today. David, go ahead.
Why does it say 12.01?
That's what we're going to get you by the end of class today. That is actually an average, and we'll talk about how we get that average in a second. Okay? All right. So, atomic mass is measured in something called atomic mass units. Pretty inventive name for it, huh? Remember, Atomic mass is a comparison. Atomic mass units are not actually a measurement. They're just a comparison. Just like yesterday on your bean lab, you got a value for navy bean to be equal to 1, and then if you did it properly, I think black beans were very close to 1, right? They maybe were like 0.8 or 0.9. But then kidney beans were like 2.2. And then lima beans were like 5 point something, right? Does that sound familiar from yesterday? That's basically what atomic mass is doing. It's comparing everything to it's comparing all the other atoms to carbon-12. But one thing that's different about atomic mass units than your value from yesterday. Carbon-12 is the comparison value, but we don't assign that value a value, or we don't assign that atom a value of 1. We assign that atom a value of 12. Exactly 12. So carbon-12 has an atomic mass of exactly 12. Okay? That's the comparison that we use for all the other atoms. Sorry, when I say comparison, I'm talking about the mass of those atoms, the size of those atoms. Okay? All right, good there. David, go ahead.
Why does it have to be carbon-12?
There's a reason, and I will explain it to you as we go along. Okay? Technically, David, we could have set up any kind of atom. Carbon-12 is pretty important to us as far as, like, you know, building blocks of life and stuff like that. I'm not exactly sure if that's the reason why we did it or not, but it's pretty important to us here on Earth. All right, good there. Okay, let's take a look at those charts there. Yes, Augustine.
Okay, I have a question back to carbon-12.
Yep.
And the number of protons, electrons, and neutrons.
Yep.
Does it have 6 protons and neutrons? Because wait, first of all, does it have 6 protons and neutrons?
So the question was about the number of protons and neutrons and electrons in carbon-12, right? First, it has 6 protons. We know that because it's what?
Carbon-12.
Well, let's go with, let's not forget about the 12 for now. We know it has 6 protons because it's what?
Oh, it's carbon.
It's carbon, and carbon's atomic number is 6.
Yeah.
So that's how we know it has to have 6 protons. Yeah, and electrons, right? The 12 that shows up after the name, that's the mass number. And we'll see how that's going to change here in just a second, okay? But mass number is the number of protons and the number of neutrons, plus, right? Plus number of neutrons. So if the total protons and neutrons is 12, but there's 6 protons because it's carbon, there has to be 6 neutrons.
Okay.
Does that make sense?
Yeah.
We're going to do a lot more of that here in just a second, okay? All right, so let's take a look at these charts that are shown up next to you, but I'm going to only have you look at part of it because the rest of it is really confusing. So let's take a look at, oh crud, sorry buddy, it's not what I wanted to do. It's going to look great on the recording. All right. So in this first table here, all I'm going to have you do is look at these first 2 columns. See, this column says natural abundance, nuclear spin, and magnetic moment. Just disregard at this point in time. If you want to cross them out, feel free to cross them out. Just for the carbon-12, though. Not for the magnesium just yet. So let's take a look here at these 2 values. All right? So, Augustine, to review what we just said, right? Here's carbon-12, okay, written in a different form, but it's still representing carbon-12. And so we just discussed that carbon-12 has 6 protons, 6 neutrons, and 6 electrons, right? Okay. Here's another isotope of carbon, carbon-13, okay? The fact that it's carbon means what about it?
It's electrons and protons.
It still has 6 protons and it still has 6 electrons. All right? But what changes now?
The
Number of neutrons. How many neutrons specifically here? 7. All right? We good with that? Yes, no? Hopefully. That part clear? Okay. All right. But more importantly, let's take a look here at this column, which is the atomic mass. Right? We just said, or I just told you, that for carbon 12, the atomic mass is exactly 12.0. Look at all the zeros after it. Okay? What happens to the atomic mass when we go from carbon 12 to carbon 13? Was that just you gone, or were you actually saying, oh, that's not. What happens to the atomic mass when we go from carbon 12 to carbon 13? Let's go generally. It goes up, right? So here's carbon 13. Here's its atomic mass, right? It goes up, and it goes up by about how much? By about 1, right? What's the only difference between a carbon 12 and a carbon 13 atom? 1 neutron makes them different, right? Meaning that each proton and each neutron counts for about 1 in the mass of that atom, right? We don't worry about electrons so much because what do we know about electrons in relation to the other two? How big are electrons compared to protons and neutrons? They're really, really small, so they don't contribute a whole lot to this atomic mass. So going up by 1 neutron takes the atomic mass up by a value of 1. Does that make sense? Good there? David, go ahead.
I heard that carbon 14 is actually radioactive.
It is. Yeah.
But there's like 100 other elements with a lot more protons and neutrons that aren't radioactive.
Correct.
How is that possible?
It has to do with the ratio of the number of protons to neutrons in a nucleus. Sometimes it's not just the straight up number, it has to do with a ratio. And if the ratio is off, that element becomes radioactive, right? Which is also, but things that are radioactive fall apart. That's the nature of radioactivity. And we'll talk about that when we get into nuclear chemistry. So there's a lot less carbon-14 around than there is carbon-12 because carbon-14 disassociates. It breaks down into carbon-12, right? So that's why there isn't that much of it around. But it's not just a straight numbers thing that if you have this many protons or this many neutrons, it's radioactive. A lot of it has to do with the ratio between the two of them. Okay? Is that good? All right. Next, let's take a look at the next table. All right. So we'll slide it down here. Let's go here. Okay. And before we talk about anything else, I want you to take 30 seconds, hopefully it doesn't take any longer than that, and with the person next to you, figure out how many protons, how many neutrons, how many electrons there are in these 3 isotopes. Go. Alright, first, any problems with the numbers that I've written up on the board? As far as identifying number of protons, neutrons, and electrons in these atoms. Good there? Good. Not necessarily, no, as long as you can tell me which is which. I don't care which order you write them in, really. So, okay. All right, but now let's start examining where we go with this, right? If we take a look at the first isotope that's up on the board. First, what would its name be? Magnesium-24, right? And magnesium-24 has 12 protons, 12 neutrons, and 12 electrons. Compared to carbon-12, we have doubled everything, right? Right? We went from 6 protons, 6 neutrons, 6 electrons to 12 protons, 12 neutrons, 12 electrons, right? However, when we look at its atomic mass, what do we see? Is it exactly double? It is not, right? If it was exactly double, what would it be? 24.0. It's not 24.0. Okay? Here, magnesium 25, right? 12 protons, 13 neutrons, 12 electrons. Again, it goes up by about 1, but it's actually a little bit more than 1 time bigger than magnesium 24. Does that make sense? Sorry. Do you see that? I don't expect it to make sense at this point in time. Okay? All right, and then the same thing with magnesium 26. So, these numbers, what do they tell you about protons, neutrons, and electrons? Nate? They are not always the same weights, right? Just like yesterday in your lab, we were counting and trying to compare beans from one another, okay? Some of you got to the very, very end yesterday, and you counted, right, Jennifer, I know you did this morning, right? The last calculation that you do, you use some numbers to try and calculate the weight of 300 beans. You then go to count that weight and see if there's actually 300. Were there? No. Why not? Are all those beans exactly the same as all the other beans? They're not. Just like all protons, neutrons, and electrons aren't necessarily the same as all other protons, neutrons, and electrons. If they were, magnesium-24 would be twice as big as carbon-12. It's not. This is measurement stuff. This is not like us coming up with theories and explanations. When we measure the mass of these atoms, we can't obviously do it individually, but when we measure the mass of these atoms, we find that they are not exactly twice as big as one another. Okay? Good there? So, atomic mass compares all of the atoms to carbon-12. All right? Next thing I want you to do, pull out your periodic table and take a look at magnesium on your periodic table. You should know where it is. You just had to use it to do your exercise before. All right? And, sorry if I'm making you dizzy. Okay. So, there's magnesium, right? The atomic mass that is listed for magnesium on your periodic table is what? What's the atomic mass listed on magnesium? 24.31. If you look at this chart and those 3 atomic masses, what do you notice? Are any of them 24.31? No. So what is this number? All right? What is this number on the periodic table? If none of the isotopes are 24.31, but this is listing 24.31, what does it mean? It's an average, all right? So, if you add up these three, okay, Eric, good. We take an average, right? If you add up these three, you'll divide by 3 and get an average, okay? I won't save you time. Peyton, do you really want to do it? All right, Peyton's going to add those 3 up and divide by 3 and give us the average. I need like some elevator music to play on the recording. So.
Wait, does the Huntington hotline ring? It sounds like elevator music.
See.
Like,
I could go. Does anybody have Time Warner Cable at their house? They have those new commercials out that their call center's faster now, so you can go to their website and listen to their old like hold music. I should have pulled that up like so we could. All right. Do you mind if I have your calculator? So can I put that on the screen? All right. So Peyton went through and she calculated the average of these 3 atomic masses, and she got 24.98. Yes? Okay. 24.98 is not what? 24.31. Right? Which is what is listed on the periodic table. So where is this number coming from? All right? And the answer is it's an average. But when we look at the rest of this chart, right? Specifically, the next column. So I'm going to slide this over here. Go here. Right? The next column is labeled the natural abundance. And it's described by a percentage. So, what do we see about the magnesium isotopes that we find out there in the real world? Are they distributed nice and evenly?
No.
They are not. There is not the same number of magnesium 24s and magnesium 25s and magnesium 26s. So when we take the average, we can't just take these 3 added together and divide by 3, because there's more of these than there are the other 2. If there's more of the magnesium 24s, what does that do to the average? If you have a bunch of 80s and 190, is your grade in a class going to be 85? No, it's going to be closer to what? It's going to be closer to, if you have a bunch of 80s and 190, what's your grade going to be closer to? It's going to be closer to 80, right? Because each of those 80 grades brings the average down. Here, there's a lot more magnesium 24s than the other 2. And that brings the average closer and closer and closer to the mass of magnesium 24. All right? We refer to that number on the periodic table, and your periodic table should refer to this as well, as the average atomic mass. It's not atomic mass, it's average atomic mass. As we just saw from that chart that we were looking at, not all of the isotopes occur naturally in the same proportions. Some occur more often than others. Average atomic mass takes into account the distribution of the different isotopes and the atomic mass of each. So how much does each weigh plus how often does it show up? That number on the periodic table takes into account both of those things. What is the atomic mass of each isotope, and does one of them show up more often than the other ones? Good there? All right. I think that's a good place for us to stop today. There is some homework on the calendar for tonight, but I think I'm going to push it back to tomorrow because we didn't quite get as far as I wanted to today. That's all right. We'll finish this up tomorrow and start doing some math things in class, okay? So I'll adjust the homework on the calendar tonight, move it to tomorrow.